Hello! In this video I'd like to talk about deterministic root-to-leaf tree automata. The directionality situation with tree automata is very different from the directionality situation with ordinary word automata. We can easily imagine how we would take the definition of an automaton that reads words from left to right and modify it to give us a notion of automaton that reads words from right to left. When we make this modification, of course, it changes what automata accept what words. They're going to accept the reverse words now, but it's not going to change what constitutes a regular language. Anytime we have an automaton that reads words from left to right, we can find a reversal for that automaton that reads words from right to left that accepts the same words. The easiest way to see this is in terms of regular expressions or non-deterministic finite state automata, particularly in terms of either paths through graphs or triangular constraint systems. But with tree automata, we're going to have to make some sort of structural change to how these things work, even to be able to make sense of the definition of a root-to-leaf tree automaton. And it will also happen that reversing the direction changes the expressiveness of the automaton. So we're going to define deterministic finite state root-to-leaf binary tree automata as a tuple, again, where we have a finite set of characters, a finite set of states. In this case, we're going to want to have a start state, and we're going to have some sort of transition function, which I'll specify later, and we're going to want to have some sort of final set. We'll see about this later. So suppose that we have some sort of rooted labeled binary tree. We're going to, starting at the root, assign states to all of the different nodes of the tree. And we're going to start off by assigning the root the start state. So let's say that for a particular automaton, the start state is state 0. So our transition function is going to take in 3 inputs. It's going to take in the state at a particular node, the character at that particular node, and some sort of indication of what shape the tree looks like going down from that particular node. So in particular, does it have a left child? Does it have a right child? Before, when we were talking about deterministic leaf-to-root tree automata, the transition function got this information automatically based on which of the children actually had a state to pass to it. Remember that we passed an octothorpe when we were missing either a left child or a right child. But in this case, there's always going to be a parent node, so we want to give it the same sort of information. We want to tell it whether or not there's going to be a left child and whether or not there's going to be a right child. And so I'm going to input that information as just a symbol indicating what the tree looks like at this particular point. Either an indication that there's both children, or just a left child, or just a right child, and I'm actually going to handle the leaves separately. And so when we pass the transition function, this indicator here, that tells us that we have a left child and a right child, so we need 2 states. We need a state for our left child to go into, and a state for our right child to go into. So in order to figure out what states to associate to this node here and this node here, we're going to want to look up delta of 0a, because that's the state at the parent node, and the character at the parent node, and then this symbol here to indicate that there's both a left and right child that we need to know the states for. Let's say that this gives us 0, 1. So we're going to associate a 0 to the left child and a 1 to the right child. Next, let's say we want to work out what the states for these 2 nodes are. We're going to want to look up delta of 1a, and then the symbol indicating that we have both a left and right child. And let's say that this is 1, 1. Then we're going to associate 1s to both of these here. And of course, if we have some sort of configuration where we have a node that only has, let's say, a left child, then we're going to want to feed that information into the transition function. We'll feed in the state at the parent node, the character at the parent node, and a symbol indicating that there's only a left child. This will give us a single state which we'll want to associate to the left child. So in order to work out what state to associate this child to, we're going to want to calculate delta of 0b and an indicator that this node only has a left child. And this will return a single state, which is the state that we want to associate to this node here. Let's say that it's 1. And then finally, to work out what state we should associate to this node here, we're going to want to look up what delta of 1a and then a symbol indicating that we only have a right child is. And let's say that that's 0. So starting at the root and working our way down to the leaves, we're going to do this association. Notice that we haven't used the information yet of what symbols are at these various leaves. And we'd like to incorporate that information. We'd like our automata to be able to see those pieces of information. So what we're going to do is we're going to ask, is the pair, the state and the symbol, in the set of accept states? And this is going to have to be true for every leaf. So in order for the automaton that has this as part of its transition function to accept the tree that we originally had, it needs to be the case that the set F of acceptable state symbol pairs contains all three of 0b, 1b, and 1a. All of the leaves have to sign off their OK with the run that they've seen. It's worth noting that I've made up this definition by adapting a definition for a slightly different sort of deterministic root-to-leaf tree automaton. And so there are various ways of defining these things. And some of them are equivalent, and some of them are slightly different in terms of their expressive power. But ultimately, pretty much everything I have to say about deterministic finite state root-to-leaf tree automata is true regardless of the specifics of the formalism. Just be careful if you're looking at a particular source that they're using the same definition that I am, or if it's different, you might have to do a little bit of working out what the specific differences are between these things. This is one of the tricky bits of finite tree automata not being talked about nearly as much as finite word automata. But there is a reason why we specifically don't talk about deterministic root-to-leaf tree automata that much, and that's because they're not as expressive as deterministic leaf-to-root tree automata. Let's say we're trying to build a deterministic root-to-leaf tree automaton that takes in a tree and accepts it if it has an odd number of A's in it. We saw in the previous video that this was something we could do with deterministic leaf-to-root tree automata, and so hopefully we'd like to be able to do this with deterministic root-to-leaf tree automata. So suppose that we have such a deterministic root-to-leaf tree automaton, and we're running it through a tree, and let's say that the root node is labeled with an A, and we're going to give it a state 1 to indicate that we're hoping that what we see below it, this whole tree here given by this particular node, has a number of A's congruent to 1 mod 2. Now, what we want to check is whether or not this subtree and this subtree have the same parity in terms of their number of A's. They can either both have an odd number of A's or both have an even number of A's. But it can't be the case that one has an odd number of A's and the other has an even number of A's. And somehow we'd like to pass that information on when determining what states to associate to this node here and this node here. We could, if we wanted to, maybe hypothetically send some sort of information that said, we're hoping that there's an odd number of A's in this subtree here. But that's not what we're hoping. We would be perfectly fine if there was an odd number of A's in this subtree here, or if there was an even number of A's in this subtree here, as long as it's the same as in this subtree here. So there's really no way of passing that information in. Somehow we would like this subtree to be able to talk to this subtree. We'd like to be able to work out the parity of the number of A's in this subtree and then pass that information along so that this subtree could use that information. But we don't get that. The only time that these two subtrees connect to each other at all is through this, and they don't have the ability to talk to each other. We're just kind of passing information into both of them. We're not passing information from one of them to the other. And ultimately, these two subtrees don't talk to each other at the end. Remember that we're just checking to make sure that all of the leaves with their state symbol pairs are in the F. So there's no talking between the leaves. There's no time where this tree here talks to this tree here. This is very different from the deterministic leaf-to-root tree automata, where we were constantly having information merged together, kind of all flowing towards the root. We had information about this subtree and information about this subtree, and they could be merged together when determining the state for the root. So hopefully you see that as an intuitive explanation as to why deterministic root-to-leaf tree automata can't tell us whether or not there's an odd or an even number of A's in a particular tree. I'll show you later on in this video a more concrete way of proving this. But hopefully that's good intuition. And this also gives us the intuition that maybe we should be considering non-deterministic root-to-leaf tree automata. Remember that we would be perfectly okay if this subtree had an odd number of A's and this subtree had an odd number of A's, or if this subtree had an even number of A's and this subtree had an even number of A's, but not if one had one and one had the other. And luckily that's exactly what non-determinism gives us. So in order to turn our deterministic automata into non-deterministic automata, we're going to want to make two changes. First of all, we're going to want to change the start state to a collection of possible start states. So starting at the root, we will assign it some start state in our collection of possible start states. And then as we work our way through the tree, our transition function isn't going to give us just one possible pair of states or just one possible state to wind up in. It's going to give us a set of possible pairs of states or states to wind up in, depending on whether we ask for two states or just one state. What this is going to do is it's going to give us potentially lots of different runs with lots of potential start states and lots of potential transitions that we have to check. So in this case, we can express that we're hoping for this subtree to have a number of A's that's congruent to 0 mod 2, and this subtree has a number of A's that's congruent to 0 mod 2, or they're both congruent to 1 mod 2. Right? Our transition function gives us two possible pairs of states that we could wind up going into. Could either be the case that the left child gets state 0 and the right child gets state 0, indicating that we're hoping for an even number of A's in this subtree and an even number of A's in this subtree, or both of the children get the state 1, indicating that we're hoping for an odd number of A's in this subtree and an odd number of A's in this subtree. And again, using non-determinism, we try all possibilities. We'll try assigning state 0 to this node and state 0 to this node, and we'll also try assigning state 1 to this node and assigning state 1 to this node. And because this is non-determinism, if either of these two attempts winds up working, we wind up accepting. So if there's any way of making the choices that we're allowed to make at each step, when it comes to the final set of state symbol pairs, nothing's changed, right? We're hoping that with our runs, all of the leaves, if we look at the state associated to that leaf and the symbol at that leaf, that shows up in our set of acceptable state symbol pairs. And if there's some way of making our choices so that all of the leaves wind up in acceptable state symbol pairs, then we wind up accepting. And you can make exactly the same sort of modification for our deterministic leaf-to-root tree automata. I guess there is no start state for those, so we don't need to worry about that. But again, we just have our transition functions output, instead of a single state that we could wind up in, output a set of possible states that we could wind up in. And again, you're just checking if there's some run that gives you an accept state associated to the root. I'll talk more about these non-deterministic automata in the next video, but it's worth taking a moment to think about actually non-deterministic root-to-leaf tree automata and non-deterministic leaf-to-root tree automata are pretty much the same. They're just specifying valid configurations of a parent node's symbol and state and the child node's states. And then we're just hoping that there's some sort of association of states to all of the nodes in the tree, such that anytime we look at a parent node and its children nodes, the configuration falls within that finite set of allowable configurations. So there's really no difference between non-deterministic root-to-leaf tree automata and non-deterministic leaf-to-root tree automata. And it's worth noting that exactly the same power set determinization procedure that we had when we were proving that deterministic and non-deterministic word automata were equivalent to each other allows us to show that deterministic leaf-to-root and non-deterministic leaf-to-root tree automata are equivalent to each other. We just have a deterministic leaf-to-root tree automaton that keeps track of, at each node, the set of possible states we could be in a run of the non-deterministic tree automaton, and then checks to see if the root node winds up getting associated to some set that contains an accept state. So deterministic and non-deterministic finite state leaf-to-root tree automata are equivalent to each other. So we have these three types of automata that are all equivalent to each other, and this one type of automaton, the deterministic root-to-leaf tree automaton, that's kind of left out because it isn't expressively equivalent, right? It can't do certain tasks, specifically tell us if there's an odd number of A's within a particular tree, that these other types of automata can do. And so typically we wind up ignoring deterministic root-to-leaf tree automata and just focusing on the other three types of automata, which are all expressively equivalent to each other. So what sorts of tasks can we do with deterministic root-to-leaf tree automata? The idea here is that when we accept a particular tree word, it needs to be the case that all of the leaves wind up in acceptable state symbol pairs. We can work out what state to associate to each leaf without looking at most of the tree, just focusing on the path from the root to that particular leaf. Right? When we ask this information here, we can just ignore the information that we don't care about. Let's say that we're trying to follow a path, and if we go to the left, we wind up getting to the leaf that we're focused on for the moment. Then we don't care about the state that we associate to the right child here. We can just focus on the fact that we wind up getting this state here to the left child. And so we can work our way down the path from the root to the leaf, keeping track of the information that we do need to feed to the transition function. We need to feed in, of course, we need to keep track of the states as we go along. We need to feed in the characters that we see along that path, and we also need to feed in the shapes that we see along that path. And that's it. If we have that information along the path from the root to the leaf, that's enough to work out what state that leaf should be in. And of course, once we know the symbol there, we can tell whether or not that particular leaf winds up in the except set, and we're hoping that every leaf winds up in the except set. So I'm going to call this information altogether a decorated path. It's going to contain the information, the list of the characters along the path, the directions that we go along the path, and the shapes that we wind up seeing as we go along that path. And so, for instance, when we're looking at this labeled tree here, if we want the decorated path for this path from the root to the leaf, we can present this information like this. Again, knowing the decorated path is enough to determine the state at a particular leaf, and of course it's going to contain information about the character at that leaf, so it's going to tell us whether that leaf winds up in F or not. So the idea is that for any deterministic root-to-leaf tree automaton, there's going to be some set of good decorated paths. Let's call it P. This is just going to be the set of paths that wind up ending with a state symbol pair that winds up in F. And our deterministic automaton is going to accept if and only if all decorated paths of the input tree are in P. And this actually severely limits the sorts of languages we could talk about. Suppose that we wanted to talk about a language that just consisted of two tree words, this tree word and this tree word. This seems like a perfectly reasonable thing to do. When we were talking about regular languages of words, any finite collection of words is a regular language of words. And so one hopes that exactly the same thing is true for tree automata. One hopes that any finite collection of tree words can be the set of accepted tree words of a particular automaton. And this is actually true if we're talking about deterministic leaf-to-root tree automata or non-deterministic tree automata. But for deterministic root-to-leaf tree automata, for the ones that aren't quite as nice, this particular language that contains just these two tree words is not the set of accepted tree words for any deterministic root-to-leaf tree automaton. Why is that? Well, let's take a look at what the set of good decorated paths has to look like for an automaton that accepts these two tree words. It's going to have to contain this, right? Because this is a decorated path that we see here. It's going to have to contain this because this is a decorated path that we see here. And it's going to have to contain these two decorated paths as well. And this is hopefully our set of good decorated paths for our deterministic root-to-leaf tree automaton. But if these are all accepted paths, then this particular tree, all of its decorated paths are good decorated paths, right? We have this path here, which is this one here, and we have this path here, which is this one here. So if these two words are accepted, then this word also has to be accepted by our deterministic root-to-leaf tree automaton. And so there's no deterministic root-to-leaf tree automaton that just accepts these two labeled trees and nothing else. So again, deterministic root-to-leaf tree automata are not something we're interested in studying. We're interested in studying non-deterministic root-to-leaf tree automata, and we're interested in studying deterministic and non-deterministic leaf-to-root tree automata. But this particular case, it's not expressively equivalent to the other three, and it also can't express some really basic things that we'd really like to be able to express. I encourage you to try defining a deterministic leaf-to-root tree automaton that accepts these two trees and nothing else. So thanks for watching. In the next video, I hope to give you a bunch more perspectives on non-deterministic tree automata. In the meantime, leave any questions or comments you might have down below, and be kind to each other.